Okay, we continue from last week with this problem that we began. If you remember, it was from 2016. We did the first part. And we continue with the second part, which concerns aldehydes and ketones. And through this problem, we can revise all there is to know about aldehydes and ketones. All right, so it says now 7 reaction types are listed: addition, substitution, oxidation, elimination, hydrolysis, condensation, and reduction, which is roughly all the chemical reactions that we usually discuss. All right. Now, name the type of reaction involved when Tollens reagent is used to identify an aldehyde. In fact, these 4 parts here concern all the tests that they are involved to identify aldehydes and ketones and their oxidation and reduction reactions that are involved with this species. Now let's see. So Tollens reagent. The Tollens reagent, remember, is when it's a aqua solution of silver nitrate, which is dissolved in quite a lot of in excess of ammonia to make the solution alkaline. That is because it's important if the solution is alkaline or acidic. And okay, name the type of reaction involved when Tollens reagent is used to identify an aldehyde. Now, well, this is obviously an oxidation, the oxidation of aldehyde or the reduction of silver in the reagent. But let us here I have this picture here, which concerns this kind of test for aldehyde, because if there is aldehyde in our sample, then we're going to see this silvering of the container of our sample, in this case in the test tube. But if it's a ketone, it will not happen, does not react with this reagent. So let us see, maybe we can write down about this test for the presence of an aldehyde. Here is what will happen if under alkaline conditions, and this is important. In our case, these are alkaline conditions because they're talking about the excess of ammonia solution. Well, usually, this is what they mention in the book. And in this case, we see here, this is an aldehyde. It will oxidize, and this will be the result. This will be the anion that will form from the aldehyde, which will be part of some salt. So under alkaline conditions, there will be a salt formed, and this is the anion of this salt, and we can see the extra oxygen from the oxidation of the aldehyde. And okay, this represents the oxidation of this aldehyde. This is the oxidation half reaction. Oxidation half reaction. And obviously at the same time, when we have an oxidation, we have also a reduction, which means that the silver in the solution will, the silver ions will reduce to become silver metal, and this silver metal is what we see here in this silvering of the test tube. It looks like a silver mirror. So the aldehyde is oxidized, obviously, and the silver cations are reduced to silver metal, and this is an indication now that this is an aldehyde and not a ketone. So name the reaction. Well, here you don't need to explain all that. We just took the advantage of the question. Name the type of reaction. The reaction. This reaction is, we can say, it's oxidation and reduction. We can say they will accept either oxidation or reduction. But if we think that we are interested in the aldehyde, we can say oxidation the aldehyde, we can say. And also reduction, because these two go together, isn't it? All right. So oxidation or reduction would be an acceptable answer to this question, and you see just 1 mark. Okay. So remember, the Tollens agent can help to distinguish between an aldehyde and a ketone. It's actually the first time that aldehydes and ketones react differently, behave differently. Okay, and next question. Name the type of reaction involved in the test for a carbonyl group using the 2,4 DNPH. Okay, the test for the carbonyl group. What is a carbonyl group? Remember, carbonyl group is this group that contains this double bond between the carbon and an oxygen. And this is the carbonyl group, which we find in aldehydes and ketones. It must be said that it's also found in the hydroxylic, the acids, but in the aldehydes and ketones, causes them to behave differently than acids. So that is why the aldehydes and ketones are classed as a group of their own, not together with the carboxylic acids. So anyway, so when they say the carbonyl group, our mind goes immediately to aldehydes and ketones. And what's happening now? Name the type of reaction involved in this test. Well, this test, in fact, is in page 238 in the book, 238. And you see this test tube with the orange solution. Actually, it's an orange precipitate that forms. This type of reaction is actually at the bottom of the page. It's a condensation. We can say here it's a condensation reaction. Condensation. Reaction. So here, this type of reaction, condensation. And why is it a condensation reaction? What is a condensation reaction? Is when two reactants react together, they make up one product, but in the process they eliminate a small molecule. In this case, it's water. Condensation, yeah. That's enough here. Actually, you don't need to. I don't think you need to remember the formula for this complex compound here or this reaction, but I have prepared a picture here of the chemical reaction that takes place here. This is the what am I now? This 2,4 dinitro, where is it now? 2,4 dinitrophenylhydrazine, this molecule here, which react here is a ketone or an aldehyde that reacts. In this case, in this example, they have two alkyl groups attached to this carbon, so this corresponds to a ketone. But I mean, if the one was a hydrogen, that would be an aldehyde, if one of the two was a hydrogen. Nevertheless, what happens here, this is the 2,4 DNHP molecule that will react with a ketone or an aldehyde. And what happens is that the oxygen with hydrogen from this compound will produce. You can see here. This is going to become the little molecule that will be eliminated, the water. So this will be eliminated, and these two molecules will join in one. This is the joined molecule, and that is why this is a condensation reaction. Now, what we're going to see, actually, what we are going to observe in our test tube, if this is something that from a carbonyl group that will react with a 2,4 DNHP, there will be a precipitate formed here. I hope you can see this picture clearly. Here is the precipitate, which corresponds to this molecule that forms, and this is an indication that we have either an aldehyde or a ketone in our test tube, present in our sample. So this is a way to test for for the presence of an aldehyde or ketone, which we call collectively like the carbonyl group compounds. All right. So you see this is the carbonyl group. Okay. Then what is the next question? Question number 3. Question number 3. Name the type of reaction involved in the reaction of a ketone with sodium tetrahydroborate. Okay, so when it reacts with this compound here, when a ketone reacts with this compound, what type of reaction is this going to be? Well, this is actually the first, on page 237, from the first reactions of the ketones or aldehydes. And this corresponds to actually the reduction of ketones and aldehydes when they react. So when an aldehyde or ketone reacts with sodium tetrahydroborate, it reduces. The ketone is, or the aldehyde is reduces. And maybe we can write here the reaction. Here, I have a picture here. You see, here's an example of an aldehyde in general, and here it's a ketone. As you can see, the difference between the two is that instead of 2 alkyl groups connected to carbon, in the aldehyde, we have the one is a hydrogen, whereas in a ketone, they're both some alkyl groups. Okay, so now if this aldehyde or ketone reacts with this sodium tetrahydroborate, if it reacts with this compound, what happens is actually they reduce. And how do we write the reduction reaction in organic chemistry? We represent it with a hydrogen inside brackets, means our organic compound here, the organic compound plus if it undergoes reduction, it means that it will gain a hydrogen, which is like the opposite of oxidation, where they would gain an oxygen if they were oxidized. Now they gain a hydrogen, and we write it like that. So the product of an aldehyde become when it's reduced, this will be the product. It makes a primary alcohol because you see here that we'll have a hydrogen joining the molecule of the aldehyde, and this hydroxyl group now that produced, obviously this bond disappears, is connected to the last carbon in the molecule. That is why it's a primary alcohol. So this would be the general formula of this primary alcohol produced. But if this is a ketone, and again the ketone reduces and picks up a hydrogen, you see now the hydrogen will be, this hydroxyl group is connected now to a carbon, which is not at the end of the molecule because it's a ketone, and that is why this will be a secondary alcohol. So the result of the reduction of an aldehyde is a primary alcohol, but the result of the reduction of a ketone is a secondary alcohol. And what do we need to say here in this question? Name the type of reaction involved in the reaction of a ketone, a ketone in particular. All right. the question here? Name the type of reaction involved in the reaction of a ketone with sodium tetrahydroborate. So what did we say? It's a reduction, isn't it? A reduction, but because it's a reduction, it's always an oxidation, okay? So they will also accept if you say oxidation. So this is a reduction or oxidation reaction. Okay, I would prefer the reduction because we are referring to the ketone, which is the compound of interest, much as this one should be oxidation because we're talking about an aldehyde. Okay, so name the type, it's a reduction. Obviously, we have to choose between the choice that we have here. We cannot say a redox or something else because this is the choice and we have to choose one of these words. Now, the last question says here, name the type of reaction involved in the reaction of an aldehyde with hydrogen cyanide. Now, this one we need to talk a lot more because they like this question in terms of, because the product produced actually can have isomers and has a chiral carbon, and we need to understand very well what's going on, and we also need to understand the mechanism of this type of reaction. So, name the type of reaction involved in the reaction of an aldehyde. Now, before I tell you what type of reaction is, let's see here the choices. You see they don't have any words like electrophilic or nucleophilic or blah, 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 but it is an addition. So here it is the reaction. It's an addition type of reaction, but it's an addition. But it must be said, since it's here, the question, this is not just any type of addition, it's a nucleophilic addition, which is a very special type of addition that concerns the aldehydes and ketones. Nucleophilic addition. And I think we have to discuss about this addition. You need to look at it in some detail. But by the way, let me see in the book, this nucleophilic addition with hydrogen cyanide starts on page 237, and then in the next page they show the mechanism, the two steps of this mechanism, the nucleophilic addition. And I think, okay, let us, so what do we have? An aldehyde with hydrogen cyanide, okay. So we have an aldehyde reacting with hydrogen cyanide. And they said, what type of reaction was that? It was an addition reaction. And we said more specifically, it is a nucleophilic addition. Now, why is it so special to say nucleophilic addition? Because the addition reactions that we have seen in the past concerned electrophilic additions that would happen in alkenes with a double bond, double bond between carbon-carbon. In the alkenes, we have met, which, remember, alkenes have a double bond between two carbons, and there we have met the electrophilic addition that happened, that concerned the breaking of this double bond between the two carbons and with the addition of something. But now this addition is not an electrophilic addition that happens in the aldehydes with this hydrogen cyanide. This is a nucleophilic addition. Nucleophilic addition that we're going to see now. And this nucleophilic addition does not happen between a double bond between a carbon-carbon, but it happens in the double bond between carbon and oxygen, because aldehydes have they have the carbonyl group. So it happens in the carbonyl group here, in this double bond. This addition happens in this bond, whereas this electrophilic addition happens in this bond between carbon-carbon, and this is a big difference. And perhaps they want to check that you know where this addition happens. So anyway, so this is our concern now about the aldehyde with a hydrogen cyanide. So how can we represent this? What happens here? So let us have an aldehyde in general. in general, how can we represent an aldehyde? Remember there is the carbonyl group, of course, and the one other bond is with a hydrogen and the other with some alkyl group. So this would be an aldehyde. Okay, now look at this molecule now. This molecule is polar. Why? Because oxygen is very electronegative, and so this part here is partially negative, and the rest here, this carbon, is partially positive. Okay, and we have to show these partial charges because this is a polar molecule, and this will be important in the nucleophilic addition that we discussed. Now, we have this now is going to react with this molecule of hydrogen cyanide. You see a hydrogen cyanide molecule. How can we represent it with the bonds? It looks like that, isn't it? So for this reaction now to take place, what happens is that this bond will break, and we'll have this cyanide ion formed, which will be it's a negative ion, and of course we will also have the proton. But now it's this cyanide ion that will concern us here in this first step of the nucleophilic addition. Let me remove this electrophilic because I'll keep on saying electrophilic. So we need this is going to be now a nucleophilic addition. Remember, by the way, a nucleophile is a species that has a lone pair of electrons, isn't it? This is our nucleophile, and this is its lone pair of electrons, and we must show it. If they ask for the mechanism, we have to show this lone pair of electrons. So what happens now here is that this lone pair of electrons will attack this partially positively charged carbon, is attracted there, and obviously at the same time this double bond here will break, and the pair of electrons associated with one of the bonds will go to the oxygen. And this is now the first step, which is actually the slow step. So this is the slow step, slow step, step number 1. Okay, so what will be the result of this? It will be some intermediate formation here, some ion, organic ion, which remember here, this and this stay there. Let's say this is the hydrogen, this is the alkyl connected to the aldehyde in the first place. Here now we are going to have this cyanide ion that connected, bonded with this carbon, and of course this bond, remember, broke the one, so we have a single bond there with oxygen, but now this oxygen here is this oxygen. I'm saying now this whole intermediate thing is like a negative ion that has formed, and because of this oxygen there, this intermediate species is very highly reactive, and immediately, very fast, will react with this proton that was removed from the hydrogen cyanide, isn't it? So here, this one will react with this proton here. It will attack to this proton, and that is now, this is a very fast step now, let's say fast step, and what we are going to get, which is the step number 2, the fast step, and what we are going to get is obviously this will attract the proton there and will become a hydroxyl group. So here is the product that we are going to get. the hydrogen, the alkyl group, the cyanide ion there, and here we're going to have this hydroxy group, okay? And of course, okay, so this is what we're going to get, which is always, as you can see, this hydroxy group is always connected to carbon number 2, because we must not forget this carbon here, okay? And that is why the product is always, it has the name of 2-hydroxy, which is this one, the number of carbons there, and nitrile. This is always the product that forms, okay? Obviously, depending how many carbons we have in our chain here between the alkyl group and this carbon here from the cyanide, there will be also something else in the name of this product. But in general, it will always start with a 2-hydroxy something nitrile. What else can we say here? We are going to see later on in other problems that this carbon here, if you notice, is a chiral carbon. It's a chiral center, because if you remember what is a chiral center, is a carbon that, chiral center we call it, is a carbon that is attached to 4 different substituents. And look at this, all these 4 substituents around this carbon, they're different. This is a cyanide ion, this is a hydroxy, this is some alkyl group, and this is a hydrogen. So because all these 4 are different, this is a chiral center, and because it is a chiral center, it will have 2 optical isomers. And in other questions, in other exam papers, they ask for us, they ask us to find out, to draw the isomers, the optical isomers, and after they ask us to identify whether this is a chiral center. So these are important remarks here. In other words, that in one way or another, we're going to meet in different exam questions. So although all this story here about how the mechanism proceeds and what happens, in this particular exam, they wanted us to just say that this is name the type of reaction involved in the reaction of an aldehyde with a hydrogen cyanide, and the addition, we could say it's just an addition. But now if we go to an exam actually from 2019, a recent exam, we're going to see, I want us to go there, so in case you don't believe me that these questions do appear, look at this. It looks, ethanol reacts with a mixture of hydrogen cyanide and sodium cyanide to make this compound, which they give us its formula and its name, 2-hydroxypropane nitrate. And the reaction mechanism is nucleophilic addition, what we saw just now. Explain the meaning of the term nucleophile and so on. And here, look at this. They ask us to name the type of stereoisomers. I don't know if you have, if you see the similarity of the question. It looks, the question sounds so much different, but it's actually exactly the same thing. They give us an aldehyde. They give us the final product of the nucleophilic addition, and here they ask us to name the type of stereoisomerism and indicate with an asterisk the chiral center. So you see, it's actually the same thing. Whatever we said about that, the story, look at this. Here's the chiral center, and they ask us to decide what type of isomerism this represents, and also to draw those 2 stereoisomers somewhere, I think. But we can do that next week. So in other words, we need to make sure that we understand the mechanism of nucleophilic addition, and understand why there is this optical isomerism that happens. And this optical isomerism is particular for the aldehydes, because if it was a ketone, it's not necessarily, it will not form necessarily an optical isomers, but we can discuss this, we can continue next week, okay? So, do we have to balance the equation? Not as long as you don't even have to write down the equation, but I just wanted you to see that there is you're talking about the oxidation of this aldehyde, isn't it? So if I haven't covered the content of hydrocarbons, can I still view the video? Listen, oh, by the way, the lesson was called hydrocarbons. It should be called aldehydes and ketones, but there is some problem with the system and I cannot change the heading. So be careful, it's not hydrocarbons. And perhaps in the next week, again, it might say hydrocarbons. We are not going to do hydrocarbons. We need to finish with organic chemistry. We have to cover all the aldehydes and ketones and do something with esters and something like that. So don't worry about the name hydrocarbons, okay? It's just a problem of the system. I cannot change the heading. Sorry about that. I hope they can fix it. They were supposed to fix it from last week, but they haven't yet. So guys, I'm so sorry about this hydrocarbon story, but we can continue next week, okay? So I hope it's quite a lot of details, but anyway, slowly, with repetitions, we'll remember at the end. So bye guys, see you again.